There is a planet next door to us, almost exactly the size of a second Earth, with a day that lasts 24.6 hours and an axial tilt of 25 degrees. It once had rivers. It once had an atmosphere thick enough to hold them. And yet today, the surface pressure on Mars is less than 1/100th of Earth's. The average temperature sits at 53 degrees below 0 Celsius, and every river it ever had is gone. Not dried, not buried, stripped, lifted off the planet, one molecule at a time, over hundreds of millions of years. And the strangest part is that nothing catastrophic had to happen for it to die. It was simply too small to keep itself alive. If you are new here, welcome to Cosmeo. Hit subscribe, pour something warm, and get comfortable. Because tonight we are going to walk through exactly how Mars lost its atmosphere, its water, and its chance at a second Earth, and whether anything ever lived there before the lights went out. Now, settle in and let's ease into this one slowly. Mars is not far as cosmic distances go. At an average of 228 million kilometers from Earth, it is close enough that we have driven rovers across its surface, photographed its dust storms from orbit, and mapped dried river channels that wind through its ancient highlands. We have held rocks from Mars in laboratories here on Earth. We have listened to the wind there. In the long silence of space, Mars is practically a neighbor, and yet that neighbor is barely recognizable as a world. This is the part that takes some adjusting to. Mars is not an alien planet in the way a gas giant is alien, or the way a world orbiting a distant star is alien. It is not a stranger. It is something closer to a sibling. A sibling that got part of the same setup we did, and then lost almost all of it. Think about what the two planets share. A day on Mars lasts 24.6 hours, close enough to Earth's that early astronomers noticed the resemblance immediately. Mars has an axial tilt of roughly 25 degrees. Earth's tilt is about 23.5 degrees. That small difference means Mars has seasons. Real seasons. Winter and summer, just like here, just stretch longer because the Martian year runs nearly twice as long as ours. Mars is smaller than Earth, with a diameter of about 6,080 kilometers, or roughly 4,212 miles, but its dry land surface area is comparable to the total land area of Earth. Not similar in some rough ballpark sense, genuinely close, a rocky crust, ancient river channels, evidence of standing bodies of water billions of years ago, seasons driven by axial tilt, a day that feels almost familiar. Mars did not miss the template for habitability by a wide margin. It hit most of the early marks, and then it failed. Completely. Here's where the numbers stop feeling reassuring. The surface pressure on Mars today is less than 1/100th of Earth's average. If you stood on the surface without a suit, your blood would begin to boil, not from heat, but because the pressure is too low to keep liquids stable in the human body. The air is not merely thin, it is functionally absent by any standard that biology requires. The atmosphere that remains is almost entirely carbon dioxide, about 95.3%. The remaining fraction is nitrogen at around 2.7%, and argon at roughly 1.6%. There is almost no oxygen. There is no breathable air in any meaningful sense. What Mars has is closer to the exhaust of a planetary process than an atmosphere capable of supporting life. And the cold is not the cold of a harsh winter. It is the cold of a world that has lost its ability to hold heat. The average surface temperature on Mars is around negative 53 degrees Celsius, which is negative 64 degrees Fahrenheit. At the poles, during the Martian winter, temperatures drop to roughly negative 128 degrees Celsius, or about negative 198 degrees Fahrenheit. Those are not edge cases. They are a significant part of the planet's normal range. Now, here is the part that tends to mislead people. On a summer afternoon near the Martian equator, temperatures can briefly climb to around 27 degrees Celsius, which is about 80 degrees Fahrenheit. That number sounds livable. It sounds almost pleasant. But warmth alone is not habitability. Not warmth, not even close. With surface pressure less than 1% of Earth's, Liquid water cannot exist stably on the surface at any temperature. Pour water onto the Martian ground, and it does not pool. It either freezes instantly or vaporizes. The thin air cannot hold it in liquid form. That brief warmth at the equator is real. What it does not mean is that Mars is a world in rough shape that just needs some warming up. This is the central thing to understand about modern Mars. It is not a damaged version of a healthy planet. It is the collapsed remains of something that once functioned very differently. Billions of years ago, Mars almost certainly had a thicker atmosphere. Liquid water ran across its surface. The evidence is still there in the geology, in valley networks that only running water could have carved, in the remnants of what appear to have been ancient lake beds, and possibly even shallow seas. Whatever those early conditions were, they were different enough from today that the comparison is almost disorienting. Something happened. Something stripped Mars down to what it is now. The planet that stands at the start of this question is a world of deep red dust, bone-dry channels, and air so thin it would kill you before you could feel the cold. It is close enough to map in detail, close enough to study with machines we built in the last few decades. It is the best second option we have, and it is telling us something important about what a planet can lose, and how fast. What it lost, and why it could not hold on, is the question the rest of this journey is built around. Stay with that for a moment. Close enough to map. Close enough to drive across. Close enough that the question stops being abstract and becomes something almost uncomfortably specific. Because the question matters. And the right question is not the one most people start with. For a long time, the central debate about Mars was simple. Was there ever water? Did the planet once hold liquid on its surface? That question has an answer now. The answer is yes. Mars had rivers. It had lakes. It had groundwater moving through rock layers deep beneath the surface. It had minerals that only form when water sits long enough to alter the chemistry of the surrounding stone. It had an early interior that was geologically active, generating heat, driving processes, creating the conditions that liquid water needs to persist. The evidence for all of that is written into the landscape in a dozen different ways. So that question is closed. And here's where the inquiry changes shape. Because knowing that Mars was once wet does not actually tell you the most important thing. It tells you what was there. It does not tell you why it could not stay. The harder question is this. How does a planet accumulate rivers and lakes and groundwater and active geology, build all of that over hundreds of millions of years, and then lose it? Not lose some of it. Not thin it out gradually over time in ways that barely register. Lose it so completely that what remains is a frozen desert with an atmosphere so thin it barely qualifies as an atmosphere at all. That is the question the evidence is actually pointing at. And the stakes of that question are higher than they might first appear. A world can get surprisingly far toward habitability and still fail to hold the conditions that maintain it. That is the unsettling implication written into every dry river channel and every ancient lake bed on Mars. The planet did not fail at the beginning. It was not always a desert. It built something. It built what looked, in the early solar system, like the beginnings of a viable world. And then the system that maintained all of that broke down. This is why Mars matters. Not simply because it was once wet. Many bodies in the solar system carry water signatures. Asteroids carry ice. Moons orbiting the outer planets hold liquid oceans under their surfaces. Water is not rare. What Mars offers is something more specific. It got close enough to the conditions that define a habitable world to show us how much a planet can actually lose. That is a different lesson, and it is a more important one. Think about the comparison that sits at the center of this. Earth and Mars both formed out of the same disk of material, circling the early sun. The same neighborhood, the same raw ingredients, rocky planets, similar in class, orbiting in a region of the solar system where liquid water was at least plausible. In the first 100 million years or so of solar system history, The two planets were not as different from each other as they are now. Both had atmospheres, both had liquid water at the surface, both had active interiors generating heat. One of them stayed that way, one of them did not. That asymmetry is the real problem. If Mars had simply never had the ingredients, the story would be less interesting. You could look at it the way you look at the outer planets, as worlds that were never candidates to begin with. But Mars had the ingredients. It had rivers and lakes and chemistry and heat. The failure was not in the starting conditions. The failure was somewhere in the system that was supposed to hold those conditions together. Something that worked on Earth, that still works on Earth today, did not work on Mars, or worked for a while and then stopped. That is the question the rest of this journey is built around. Not whether Mars had water, but how a planet that had so much of what it needed ended up with nothing. Whatever the answer turns out to be, it tells us something that extends beyond Mars. It tells us something about how planetary systems succeed or fail. About how thin the margin is between a world that holds onto its conditions and a world that does not. And about why Earth, sitting in the same part of the same solar system, is still here to ask the question at all. The gap between what Mars was and what Mars is now is enormous. And somewhere in that gap is the most important part of the story. Let's think about what couldn't hold it together actually means at the level of the planet itself. Mars and Earth formed at the same time, about 4.5 billion years ago, from the same disk of gas and dust, in the same neighborhood of the young solar system. Mars went through the same process Earth did. It differentiated, meaning it organized itself into layers, with a crust on the outside, a mantle in the middle, and a core at the center. It was a real rocky planet from the start. Not a failed experiment, not a half-formed world, a planet. So the question is not why Mars formed wrong. It didn't. The question is why it couldn't sustain what it built. The answer starts with a single number. Mars has roughly 1/10 of Earth's mass. Not half, not a quarter, 1/10. And its surface gravity comes out to about 38% of Earth's. That means if you weighed 180 pounds on Earth, you would weigh about 68 pounds on Mars. The planet is not just smaller, it is dramatically less massive. And that difference, which sounds like a simple measurement, set the terms of almost everything that followed. Here is why mass matters in a way that goes deeper than size. A smaller planet loses its internal heat faster. The physics of this is straightforward. A small object has more surface area relative to its volume than a large object does. Heat escapes through the surface. So a smaller planet radiates its internal warmth into space more efficiently, relative to how much heat it has stored. Think of a small cup of tea next to a large pot of boiling water. Both start hot, but the cup cools in minutes. The pot stays warm for much longer. Mars and Earth are versions of the same comparison. Both started with enormous internal heat from formation and from the decay of radioactive elements in the rock. But Mars, the smaller vessel, began losing that heat faster from the beginning. That internal heat is not just about keeping the interior warm. It drives everything. It powers mantle convection, which is the slow churning motion of rock moving through the planet's interior over millions of years. Mantle convection drives volcanism, which means it drives the volcanic outgassing that built Mars's early atmosphere. And critically, it drives the planetary dynamo. The dynamo is the mechanism by which a planet's liquid metal core, moving and churning from thermal energy, generates a magnetic field around the planet. On Earth, that dynamo has been running for billions of years. It produces the global magnetic field that surrounds us right now. On Mars, those systems weakened much earlier. Not suddenly, not in a single catastrophic event, but gradually, steadily, over hundreds of millions of years. The planet was not weak from the start. It was losing resilience. There is a difference. But here's where it gets strange. In 2021, NASA's InSight lander, which had been recording seismic activity on Mars for years, sent back data that surprised the planetary science community. Mars still has a liquid core, a molten interior with a radius somewhere between about 1,590 and 1,850 kilometers, or roughly 112 to 150 miles. The core did not freeze solid. It did not fully solidify the way some models had expected. It is still there, still liquid, still warm, and yet Mars has no global magnetic field today. That is not how the story was supposed to go. A liquid metal core is supposed to generate a dynamo. Earth's liquid core generates ours, so why isn't Mars generating one? The core is liquid, but apparently it is not convecting the way it needs to. It is not churning with enough motion to sustain the large-scale electrical currents that create a magnetic field. The heat is there, but the motion is not, or not enough of it. Why that happened is a question the science has not fully resolved. We will come back to it. But for now, the point is this. A liquid core without a working dynamo is a planet that lost something critical even before its interior solidified. Whatever stopped the dynamo running on Mars, it stopped long ago. Now, none of this means Mars was geologically boring. It was not. Olympus Mons sits on the Martian surface at roughly 26 kilometers high, or about 16 miles. That is the tallest volcano known anywhere in the solar system, 3 times the height of Everest, so tall that its peak reaches above most of the Martian atmosphere. And then there is Valles Marineris, a canyon system that stretches more than 4,000 kilometers across the planet's surface, or more than 2,500 miles. To put that in terms of somewhere familiar, if you placed it on a map of the United States, it would reach from California to New York. These are not small features. These are the largest structures of their kind we have found anywhere. Mars did not lack geological power. It could produce extremes. What it could not produce was the endurance to keep its planetary systems running long enough for that early habitability to last. That distinction matters. Mars was not boring. Mars ran out of time. And when the internal engine weakened, it set a cascade in motion. A smaller world loses internal heat faster. A world that loses internal heat faster has a harder time sustaining the dynamo that generates a magnetic field. A world without a strong magnetic field has a harder time protecting its atmosphere from the solar wind. The constant stream of charged particles flowing outward from the sun. An atmosphere exposed to the solar wind for long enough begins to erode, and a planet with a thinning atmosphere loses the pressure needed to keep liquid water stable at the surface. One link follows the next. Smaller world, faster cooling, weaker internal engine, loss of magnetic protection, atmosphere eroded, surface water unstable, gone. The first weak link in that chain may have been size itself. That is what we are tracing through the rest of this story. Not a single disaster, not one bad event, a cascade that began in the physics of mass and heat and played out over billions of years. And the next question is where that cascade first became visible. The cascade became visible on the surface. Mars is dry now. The air carries almost no moisture. There are no rivers, no lakes, no oceans. A handful of dust devils trace across plains that have been waterless for billions of years. If you stood on the Martian surface and looked out at any direction, you would see nothing that looked alive with water. And yet the surface itself tells a different story. Not a subtle one. Not a story you have to strain to read. A story written clearly in the shape of the land itself. The first thing that catches the eye from orbit is the valley networks, branching drainage systems carved into some of the oldest terrain on Mars. These are not shallow scrapes or minor features. They are organized, tree-shaped systems, wide channels that split into smaller channels, which split again, exactly the way a drainage network behaves on Earth when rain falls on a hillside and finds its way downhill. The pattern implies something specific. Ice alone does not carve that shape. Wind does not carve that shape. Flowing liquid water does. These valleys trace back to the Noachian period, the oldest chapter of Martian geological history, which ended roughly 3.7 billion years ago. That was a time of heavy impacts, strong erosion, and major valley formation. Scientists think the valleys were cut by surface runoff and possibly groundwater working its way upward through the rock, a process called groundwater sapping. Rain and snowmelt may have fed them. Hydrothermal systems, heat from the interior driving water upward, may have contributed as well. The exact mechanism is still debated, but the shape is not in dispute. Branching valleys do not form in isolated wet moments. They require an active hydrological system, water falling, flowing, accumulating, and cutting its way through rock over time. That is the surface record from orbit. Then the rovers reached the ground. Curiosity landed in Gale Crater in August 2012. Shortly after it began driving, it encountered something that geologists immediately recognized. Smooth, rounded pebbles. They were sitting in an ancient streambed, and their shape told a precise story. Rocks do not round themselves sitting still. The only natural process that rounds a rock that way is transport in flowing water, the constant bumping and tumbling as a current carries it along. The rounder the pebble, the farther it has traveled. These were well rounded. NASA's interpretation was direct. Those pebbles had likely traveled at least a few miles in a real stream. And from the size of the pebbles and the way they were arranged, scientists estimated the stream depth. Ankle deep to hip deep. Not a trickle, not a wet patch left behind after a storm. A stream you could have waded through. That is the kind of evidence geologists trust. Not because Mars is like Earth in every way, but because the physical process is the same. Water rounds rocks on Earth. Water rounds rocks on Mars. The physics does not change because the planet does, but something was wrong. Rounded pebbles are compelling, but they speak to a moment. They tell you water moved here in this place at some point. They do not, by themselves, tell you how long the water lasted. A single rainstorm could theoretically deposit rounded pebbles if the runoff was powerful enough. So the question remains, was this a long-term environment or a lucky exception? Curiosity kept climbing. Gale Crater is not flat. Its center holds a mountain of layered rock several miles high, and Curiosity spent years ascending through those layers, reading them the way a geologist reads pages. What it found in those layers was not occasional water. It was more than 1,000 vertical feet of mudstone. That is more than 300 meters of rock, formed from fine sediment that settled slowly at the bottom of shallow lakes. Mud does not fall out of moving water. It settles when the water goes still and stays still long enough for the finest particles to drift to the bottom and compact. Layer after layer after layer. That kind of record does not write itself in a week or a year or even a century. NASA concluded that the rivers and lakes in Gale Crater may have persisted for 1 million years or longer. Let that number sit for a moment. 1 million years is not a lucky accident. 1 million years is not a planet that briefly warmed, spilled some water, and froze again. 1 million years is a stable environmental regime. 1 million years means conditions held long enough to build a real sedimentary record. The kind of record that preserves chemistry, preserves mineral signatures, preserves the conditions that existed at the bottom of that lake while it was full. On Earth, sedimentary records like this are where scientists go to read ancient environments. Mars had one, a deep one, and Gale Crater was not the only place. Before Perseverance landed in Jezero Crater in February 2021, orbiters had already seen something from above that left little room for interpretation. A delta. A fan-shaped deposit of layered rock spreading out from an ancient channel mouth at the crater's edge. Deltas do not form casually. A delta requires 3 things working together: moving water, carrying sediment, a standing body of water for the river to flow into, and conditions stable enough for organized sediment buildup to accumulate over time. If any one of those 3 things is missing, you do not get a delta. You get a mess or nothing. Jezero had a delta, a well-preserved one. By late 2023, NASA was describing Jezero as an ancient river and lake system that Perseverance had traced from beginning to end. Not speculated, traced. The rover had driven across the delta, sampled its layers, and followed the ancient shoreline. The picture that emerged was complete. Channels feeding water downhill from the surrounding highlands, a lake filling the crater, a delta building at the point where the river met the standing water. The whole system preserved in rock. Stack the evidence together and the picture it builds is not subtle. Valley networks carved across ancient terrain by flowing water in organized drainage systems. Rounded pebbles transported miles by real streams of ankle-deep to hip-deep water. More than 300 meters of mudstones settled at the bottom of lakes that persisted for at least 1 million years. A fully developed river delta lake system preserved at Jezero. Each piece of evidence speaks to a different part of the hydrological cycle. The valleys are the drainage system. The pebbles are the transport. The mudstones are the persistence. The delta is the full architecture. Together they are not ambiguous. Mars did not have occasional dampness. Mars had functioning hydrological environments that operated long enough to write themselves into the rock in detail. The surface is a preserved archive, and the archive is still there, waiting to be read. What it records is a planet that once held water the way a planet should, not in flashes, not in traces, but in rivers and lakes and deltas that lasted long enough to matter. The cascade that stripped all of it away left the evidence behind, and the evidence is only the beginning of what the rock holds. But the archive goes deeper than shape. The surface record shows where water moved. Valley networks trace the paths it followed. Pebble beds mark the streams it carried sediment through. Mudstone layers record the lakes it filled. All of that is the topographic record, the impression the water left on the landscape. The chemical record is something else. It is what the water did to the rock itself. When liquid water makes prolonged contact with rock, it does not just move across it, it reacts with it. Minerals dissolve, new minerals form. The chemistry of the rock changes in ways that preserve the interaction permanently, long after the water is gone. These are called hydrated minerals, minerals that incorporate water molecules into their crystalline structure during formation. They are not just evidence that water was present, they are the water locked into stone. The European Space Agency spent years mapping these minerals across the full Martian surface. What they found expanded the picture considerably. More than 10 distinct kinds of hydrous minerals appear across Mars, not concentrated in one region, not limited to a handful of sites, across the planet. Earlier surveys identified several thousand individual exposures of these minerals. Later mapping, with better instruments and wider coverage, pushed that number into the hundreds of thousands of areas, most of them concentrated in the oldest terrains. That number is worth sitting with. Hundreds of thousands of areas where water changed the chemistry of the rock. Mars was not briefly damp in a few places. Water engaged with the crust of that planet on a scale that is difficult to picture. But the type of mineral matters as much as the quantity. This is where the story becomes more precise. Among the most abundant hydrated minerals on ancient Mars are clays, specifically a group that includes smectite and vermiculite. These are minerals that form through a particular kind of reaction, one where liquid water slowly breaks down volcanic rock and converts it into layered, sheet-like structures. The process takes time. It requires sustained contact between water and rock, not a brief encounter, and it requires the water to be within a certain chemical range. Here is what that implies. Clay formation does not happen in harsh conditions. Strongly acidic water, extremely salty brines, environments where chemistry is pushed to extremes, these do not produce clays in abundance. They produce other minerals. Clays form when the chemistry is relatively moderate, when the water is closer to fresh than to brine, when conditions allow slow, sustained interaction without immediate chemical destruction. For decades, the working picture of early Mars leaned toward harsh, salty, acidic, briny water. A planet where liquid water existed, but only in forms that would be chemically hostile to most life as we understand it. That picture was not wrong entirely, but the clay record complicates it significantly. Not acidic brine across ancient Mars, closer to moderate chemistry, broader windows of conditions where water and rock interacted in ways that were, by some measures, remarkably mild. The implications are not small. The kind of chemistry that allows clay formation is also the kind of chemistry that allows organic molecules to form and persist. The kind of chemistry that is less destructive to complex compounds. The oldest terrains on Mars, the ones that preserve the clay record most extensively, record a planet that was not just wet, but wet in ways that were, at minimum, less hostile than we assumed. Then the chemistry changed. This is where the mineral record becomes something like a timeline. Read the right sequence of rock layers on Mars, and you can watch the planet's water chemistry shift over hundreds of millions of years. Think of reading climate history from an ice core, where each layer records a different period of atmospheric conditions, or from tree rings, where each ring carries information about the year it formed. Mars carries something similar, written in mineral transitions instead of ice or wood. In the older terrains, clays dominate. In layers that correspond to the late Noachian period and afterward, the mineral story shifts. Sulfates appear in quantity. Sulfates are salts, compounds that form when water evaporates and leaves dissolved minerals behind, or when water becomes highly acidic. They point to a different water regime, not sustained, moderate, clay-forming interaction. Instead, limited, harsher, more evaporative conditions. Water present but under stress. Water retreating. The crust records the transition directly. Clay-rich layers below, sulfate-rich layers above. A climate shift written into stone in sequence. The planet moved from a period when water was persistent enough and mild enough to form clays across vast regions, to a period when water was scarce enough and harsh enough to leave behind salts. That is not a subtle signal. It is a chemical signature of a world changing. A planet's water story condensing from wide and mild to narrow and extreme. But the surface layers are only part of the record. Water on early Mars did not stay on top of the ground. The Terrena Terra region of Mars sits in the southern highlands, ancient cratered terrain that has been geologically quiet for a very long time. ESA and NASA data identified 175 sites in that region alone where something unusual happened. Impact craters, the kind that formed when asteroids or comets hit Mars with enough energy to excavate deep into the crust, brought material up from below the surface and scattered it around the impact site. And when scientists examined that excavated material, they found hydrated minerals, waterform minerals that had been sitting underground, not on the surface at all. The depths those impacts reached ranged from tens of meters to kilometers. Think about what that means for a moment. Those minerals did not form on the surface and then get buried. They formed underground. Water was moving through the subsurface of Mars, reacting with rock deep below the surface, altering the chemistry of the crust from the inside. The impacts did not destroy that evidence. They exposed it. Craters that look at first like simple destruction turned out to be something else entirely. Not just scars on the landscape, natural drill holes, boring down through the crust and bringing the record of underground water up where instruments could read it. Underground water on Mars appears to have persisted for long periods during the planet's first billion years. The subsurface alteration is not a trace signal. It is widespread enough that 175 sites in one region of Mars preserve it in excavated rock. The system extended below the surface, not just rivers and lakes on top. A water system that penetrated the crust. The full picture that emerges from the mineral record is this. Mars had hydrated minerals forming across hundreds of thousands of sites in its oldest terrains. It had widespread clays that required moderate, sustained water chemistry. It had a transition from clay-forming conditions to sulfate-forming conditions that records a planetary climate shift over geological time. And it had underground water altering the subsurface rock at depths of tens of meters to kilometers during its first billion years. This is not a planet that was briefly touched by water. Mars was geochemically transformed by water. Not at the surface alone, not in one period. At planetary scale, across layers of time and depth, in a system that involved the surface, the near surface, and the deep crust all at once. The rock holds more of that record than we have yet been able to read. And the questions the mineral evidence raises about what came next are harder than the ones it answers. But those questions have a shape now. And the shape is no longer just about water. Water alone does not make a world habitable. That is worth saying plainly. A planet can have liquid water on its surface and still be a terrible place for life. The water could be saturated with salt at concentrations that would destroy organic molecules. It could be so acidic that the chemistry of biology simply cannot run. It could be present for 1,000 years and then gone. Duration matters. Chemistry matters. What the water was doing at a molecular level matters. So the mineral evidence from the previous section answers one question and opens another. Mars had water, widespread and persistent. But did Mars have the right kind of water, in the right chemical conditions, for long enough to matter to life? Here is where the story changes shape. Curiosity was drilling into Gale Crater's ancient mudstone layers when it found something that was not just about water. It found sulfur, nitrogen, oxygen, phosphorus, carbon. 5 of the key elements biology uses to build itself. Not in trace quantities. Present in ancient rock that had been sitting on the Martian surface for more than 3 billion years. That list is worth pausing on. Those 5 elements are the chemical alphabet of life as we know it. Carbon builds the backbone of organic molecules. Nitrogen is essential to amino acids and nucleotides. Phosphorus sits at the core of DNA and energy-carrying molecules in every living cell we have ever examined. Oxygen and sulfur weave through biological chemistry in dozens of ways. Finding them together in the same ancient sedimentary environment where we already knew water had pooled for extended periods is not proof of life. It is not even close to proof of life. But it means the habitability checklist was not empty. And the chemistry was not extreme. Curiosity also found clay minerals in those layers, the same clay types the broader mineral record had indicated, and signs of low salinity conditions. The ancient water in Gale Crater was not the harsh, concentrated brine that earlier models had assumed dominated early Mars. Some of it was closer to drinkable water, not sterile, not perfectly benign, but chemically moderate. The kind of water where organic molecules can persist without being destroyed. The kind of water where the building blocks of biology do not immediately fall apart. That is a different planet than the one scientists thought they were studying 20 years ago. But the chemistry alone was only part of the story. The other part was stability. The mudstone layers in Gale Crater do not represent a single event. Hundreds of meters of fine sediment do not accumulate in a short burst. They accumulate in repeated cycles over time as water fills and retreats and fills again, or stays and stays, depositing layer after layer of fine particles that settle to the bottom and compact. The geological record in Gale Crater implies a lake environment that was not a fluke. It returned, or it persisted, possibly both, 1 million years or longer as the earlier sections of this story established. And stability matters as much as ingredients. Life does not get started and then flourish in a single wet afternoon. It needs environments that stay suitable long enough for chemistry to build toward complexity. Gale Crater passed that test as well. Then Curiosity found something that narrowed the question even further. In 2018, the rover detected organic molecules preserved in ancient mudstones. Organic molecules, meaning carbon-based molecules of the kind that form the foundation of life's chemistry. Sulfur-bearing organic fragments. Thiophenies, which are ring-shaped compounds containing sulfur and carbon, benzene, toluene, short carbon chains, the kind of molecules that, on Earth, we associate with biology or with the chemical precursors that biology works from. Wait. Organic molecules on Mars does not mean life was there. That is the critical point, and it is easy to miss. Organic molecules can form without biology. They form in hydrothermal systems. They arrive on asteroids and comets. They emerge from purely geological chemistry. Finding organics does not confirm life existed. But here is what it does confirm. Mars had meaningful carbon chemistry. The concentration of organic carbon that Curiosity detected ran to roughly 10 parts per million or more. That is about 100 times higher than earlier surface detections had found. The old idea that Mars lacked meaningful organic chemistry, that the Martian surface was so hostile that organics simply could not survive, was wrong. Not slightly wrong. It required revision. What the organics discovery did was change the shape of the question. Before, there was a reasonable argument that even if Mars had once had favourable conditions, the chemistry simply was not there, that Mars lacked what life would have needed. That argument no longer holds. The chemistry was there. The elements were there. The water was moderate enough, persistent enough, and stable enough to matter. The remaining question was not whether Mars lacked what life could use. The question became whether anything ever used it. Jezero Crater was selected as the landing site for Perseverance, with exactly that question in mind. The choice was not arbitrary. Orbital data had shown a delta in Jezero, a fan-shaped deposit where an ancient river had carried sediment into a standing body of water. Deltas are significant for a specific reason. When a river slows as it enters a lake, the sediment it has been carrying drops. It settles. It accumulates in layered deposits that trap whatever the river was carrying. Organic material, fine mineral grains, chemical signals from the environment upstream. Deltas are natural archives. If biosignatures existed in the ancient Martian environment, a delta is one of the places they would most likely be preserved. The orbital data also showed carbonate-bearing terrain near Jezero, and carbonates are minerals known for their capacity to preserve organic material over geological time. By 2023, Perseverance had drilled into the Jezero Delta and returned data from the samples it collected. Those samples were rich in silica, phosphate, and carbonate. Silica is one of the best-known preserving materials in geology. On Earth, ancient microbes preserved in silica deposits remain recognizable for hundreds of millions of years. Phosphate, in addition to being one of those key elements Curiosity had already identified in Gale Crater, binds to organic material and helps lock it into rock. Carbonate preserves chemical signatures across enormous spans of time. The Jezero samples were not just interesting for what they contained, they were interesting for what they could hold on to. If biology had ever been present in that ancient lake environment, these materials would be among the most likely to have kept the record. Mars had moved across a threshold, not a small one. Water-shaped is one thing. A world whose ancient lakes contained the right elements, the right mineral chemistry, the right organic molecules at meaningful concentrations, in environments stable enough to persist for geological time and preserved in materials built to hold chemical records across billions of years, is something else. That is a world that was chemically plausible for microbes. Not proven. Plausible. The distinction is precise and important. But the gap between those two words is no longer filled with impossibility. It is filled with a question. And the question has weight. The samples Perseverance drilled from Jezero's delta sediments are waiting. They have not yet been returned to Earth for the kind of analysis that could take that question further. And the answer, if it exists in those samples, has been sitting in the rock for more than 3 billion years. Set the life question aside for a moment. The samples are waiting. The answer may be there. But before we can understand what Mars was capable of sustaining, we need to understand something more fundamental, Something that has been quietly wrong in almost every account of how the story ends. Mars lost its water. That is the phrase that gets repeated. And it carries a picture with it. Water rising off the surface, molecule by molecule, drifting up through a thinning atmosphere, bleeding out into space over millions of years until the planet ran dry. That picture is not false, but it is incomplete. And the part that is missing changes how you understand Mars almost entirely. The water did not all go to the same place. It partitioned. Some of it escaped. Some of it stayed. And the portion that stayed has been sitting there, largely unacknowledged, for a very long time. Start with the surface. The timeline of liquid water on the Martian surface runs through the Noachian period, the oldest chapter of Mars's geological history, ending roughly 3.7 billion years ago. That much has already come into view from the valley networks, the mudstones, the delta at Jezero. The surface system wound down, the rivers slowed, the lakes shrank, the open water eventually disappeared. But here is the part the surface record does not show. When the surface dried, the groundwater did not stop on the same day. The mineral evidence makes this clear. Crater-exposed rocks in regions like Tirrenia Terra show hydrated minerals from depths of tens of meters to several kilometers underground. These minerals formed through water-rock interaction at depth. They did not form quickly. They formed through sustained contact, chemical alteration working slowly through rock over long periods, continuing through much of the planet's first billion years. The surface and the subsurface were operating on different clocks. The surface story was ending while the subsurface story was still going. Underground water has a natural advantage. It is shielded from the thin, cold air above. It is shielded from radiation, which strips unprotected surfaces. It is insulated from the temperature swings that make the surface uninhabitable. The deeper you go, the more stable the environment becomes. On a planet losing its protective systems one by one, the subsurface would have been the last refuge, not a metaphor, a physical fact about where liquid water could survive the longest under worsening conditions. Then came Phoenix. In 2008, the Phoenix lander set down in the northern polar region of Mars. A few days after landing, its cameras caught something in the disturbed soil near the lander legs. Bright white material exposed where the lander's thrusters had scraped the surface during touchdown. The team watched it. Over the course of several Martian days, the bright material faded. It sublimated, transitioning directly from solid to vapor without melting. That behavior matched one substance precisely. Water ice. Not frost, not a trace. Direct confirmation that water ice exists in the Martian soil at accessible depths. Mars still has water. It was never a question of whether any survived. The question was always about form and location. The poles hold more. Radar observations of the North Polar region reveal layered deposits extending downward in stacked formations of ice and dust. Each layer a record of a different climatic period, the way tree rings record years of growth. The deposit is not thin. Scientists at JPL summarize the volume as roughly 1/3 as much water as Earth's Greenland ice sheet holds. That is not residual frost clinging to a cold place. That is a substantial planetary reservoir, and because it is layered, it is also an archive. Each band of ice and dust records a shift in Mars's climate, a change in axial tilt, a period of more or less dust in the atmosphere. The poles are not just where the water went, they are where the climate history is written. But the polar caps and the subsurface ice together are not the largest part of the story. Here is where the picture shifts most dramatically. In 2021, a NASA analysis pulled together the best available measurements of Mars's ancient water inventory and compared it against what could be accounted for in the atmosphere, the ice, and the observed escape to space. The numbers did not balance. The water that had escaped to space was not enough to account for the water that should have been there. The analysis put a range on what was missing. Between 30 and 99% of Mars's ancient water inventory may now be locked inside hydrated minerals in the crust. Not frozen, not escaped, chemically absorbed, bound into the molecular structure of rocks that formed through long contact with water, holding hydrogen and oxygen in their lattice the way clay absorbs moisture, the way a dry sponge pulled through water holds the water inside itself rather than letting it drain away. Mars did not just lose its water, it absorbed a large fraction of it. Even the low end of that range changes the picture significantly. If 30% of ancient Martian water is still sitting in the crust in mineral form, the planet is not what the word dry implies. It is a world where a major fraction of the original water inventory is present, immobile, locked into rock, spread across a crust that has been chemically altered by billions of years of water-rock interaction. Think about what that means for the narrative that gets told about Mars. The story has usually been told as a loss. Water arrived, things were wet, then the atmosphere thinned, the magnetic field weakened, and the water bled away to space until nothing was left. That story is not wrong about the mechanisms. It is wrong about the scale of what escaped. It assumed most of the water left. It may be that most of the water stayed. What truly vanished was something more specific. Not the water itself, the system that kept water moving. On a world with a thick atmosphere and an active interior, water participates in a cycle. It evaporates from surfaces, circulates through the atmosphere, falls as precipitation, flows downhill, soaks into rock, and re-emerges through springs and hydrothermal vents. The water is always moving. The movement is what makes it biologically and geologically available. When Mars lost its atmosphere and its internal heat, it did not drain. It froze in place. The water stopped moving. It pooled at the poles as ice. It sank into the subsurface and froze there. It reacted with minerals and locked into crystal structures. And some fraction, a fraction that was real but may not have been the majority, escaped to space as the atmosphere thinned and radiation stripped hydrogen from water molecules in the upper atmosphere. The death of wet Mars was not one clean disappearance, it was a partitioning. Some water escaped, some froze underground, some froze at the poles, and a potentially very large fraction was chemically absorbed into the rock itself, sitting there still, holding the record of a wetter world in the molecular architecture of the crust. Mars is not a planet that lost its water in any simple sense. It is a planet that stopped circulating it. The water is there. It is just no longer in a form that does anything. It has been immobilized across 3 reservoirs, ice and rock and sky, with the largest share possibly sitting in the crust, waiting. And what is waiting there may tell us more about this planet's early history than anything the surface has yet revealed. But the water being there, immobilized and still, raises a question the surface record cannot answer on its own. Why did Mars lose the conditions that kept water moving in the first place? The cascade that ended the active Martian water cycle had a cause, and that cause sits further back in time than the rivers and lakes. Before the water was lost, something else was lost first. Something invisible. Mars seems to have had a global magnetic field. Not a local one, not patches. A planet-wide shield, generated deep in the interior, extending far out into space and deflecting the solar wind before it could reach the atmosphere. We know this because of what Mars Global Surveyor found when it began mapping the planet. Locked into the ancient rock of Mars's southern highlands, the spacecraft detected intense remnant magnetization. Regions of the crust that had been permanently magnetized, like iron filings frozen in place after being exposed to a strong field. That kind of signature only forms in one way. A planet-wide dynamo, the same kind of mechanism that powers Earth's magnetic field, must have been active when that rock was young and cooling. The field was real. The rock remembers it. But that field is gone now. NASA is clear on this point. Mars does not have an appreciable global magnetic field today. What remains are those scattered, localized remnants locked in the oldest rock. The shield is not weakened. It is absent. Here is why that matters. A magnetic field does not just exist passively, it shapes how a planet interacts with the space around it. On Earth, the field created by the planet's core reaches far into the surrounding space and deflects the solar wind, a constant stream of charged particles flowing outward from the sun. The field bends that stream around the planet. It organizes incoming charged particles into the polar regions, where they produce auroras rather than damage. The bulk of the atmosphere sits beneath a kind of invisible umbrella, protected from the worst of what the sun continuously sends outward. Once Mars lost that umbrella, the sun had a much cleaner shot at the upper atmosphere. That does not mean the atmosphere disappeared overnight. Atmospheric erosion is a slow process, measured across millions and hundreds of millions of years. But the rules changed. Without the field deflecting the solar wind, charged particles could reach higher into the Martian atmosphere directly. Over time, they stripped away lighter atoms and molecules, carrying them into space. The planet went from a shielded world to an exposed one, and that exposure accumulated across geological time into something catastrophic. But here's where it gets strange. The southern highlands, those ancient cratered terrains that carry the strongest remnant magnetic signatures, are also Mars's oldest surviving surface. Later geological activity resurfaced large parts of the planet. Volcanic flows buried terrain. Impact basins reformed the northern lowlands. Wherever that happened, any earlier magnetic signatures were erased or diluted. The southern highlands survived with less resurfacing, and they are the ones carrying the fossil of the old protection system. The regions that were magnetized when the dynamo was running, and that were then left alone as the planet quieted, preserved the record. The regions that were reworked did not. That pattern tells us something precise. The dynamo did not shut down late in Martian history, after the planet had already gone through its active geological phases. It shut down early, very early, before most of the resurfacing had happened, before the late volcanic activity that built the great shields in Tharsis, before many of the events whose signatures cover the newer terrain. The southern highlands are Mars's magnetic museum, carrying evidence of a protection system that had already been lost by the time much of the rest of the planet was forming the features we can read today. Which raises a puzzle. Writing Section 3 introduced it and set it aside. Now it needs an answer. Insight confirmed that Mars still has a liquid core. The radius of that core, somewhere between roughly 1,112 and 150 miles in its measured estimate, is large enough to have continued sustaining a dynamo. A liquid iron core is precisely the kind of material that, given the right motion, generates a global magnetic field. Earth's field comes from exactly this kind of system. Liquid metal moving through the core, driven by convection, creates electrical currents, and those currents generate the field. Mars has the liquid metal. It does not have the field. The tempting conclusion is that the core must have frozen. That convection stopped because the iron solidified, killing the motion that drove the dynamo. But InSight ruled that out. The core is still liquid. So the problem is not the state of the core. The problem is its motion. A liquid core sitting still generates nothing. Sustaining a dynamo requires active convection, meaning the liquid must be circulating. Hot material rises. Cooler material sinks. That constant churning drives the field. On Earth, this has continued for billions of years. The planet is large enough, and its internal heat budget is sustained enough. That convection in the core has never stopped. On Mars, the conditions for that convection failed. Why exactly remains an open question. The details are debated. Possible factors include the rate at which Mars cooled after formation, the development of a layered thermal structure inside the core that resisted mixing, and the absence of plate tectonics, which on Earth helps drive the mantle convection that in turn influences heat flow from the core. Some combination of these factors, still not fully resolved, robbed the Martian core of the sustained energy flow and internal motion it needed to keep the dynamo alive. What is clear is the consequence. A smaller planet cools faster. faster cooling altered the interior's behavior in ways that ended convection in the core. The convection ended, and the dynamo fell silent. The dynamo's silence removed the shield, and removing the shield changed what the sun could do to the atmosphere above. Each step followed from the one before it. The cascade that eventually immobilized the water, dried the surface, and thinned the air had this moment somewhere near its beginning. Not the last cause, not even the only cause, but a critical one. The invisible protection was lost early, and everything the atmosphere endured afterward happened without it. The atmospheric collapse itself was still ahead, and it was not simple. What happened next was not sudden. It was slow, and it was relentless, and it never really stopped. With the shield gone, the atmosphere above Mars was no longer protected from what the sun continuously sends outward. The solar wind, that constant stream of charged particles flowing out from the sun in every direction, now had a clear path to the Martian upper atmosphere, and it used it. Over millions of years, then hundreds of millions, then billions. The solar wind stripped atoms and molecules from the atmosphere and carried them away into space. Not a dramatic explosion, not a single catastrophe. A slow, sustained campaign of erosion that never let up. NASA's MAVEN mission, the Mars Atmosphere and Volatile Evolution spacecraft, spent years measuring this process directly. What it found was not theoretical. The loss is active. Solar wind and radiation are responsible for most of the atmospheric loss Mars has endured, and that loss is still measurable today. The thin atmosphere pressing down on Mars right now is not the natural state of the planet. It is the leftover fraction, a survivor. What Mars once had was substantially thicker, and what remains is what the sun could not carry away. Think about what that means for the surface. As the atmosphere thinned, surface pressure dropped. And as surface pressure dropped, stable liquid water became harder and harder to maintain. The climate that supported early Mars, the conditions that allowed rivers to flow and lakes to persist for 1 million years at a stretch, did not end because of a single bad event. It slid away, gradually, persistently, episode by episode, as the air above thinned and the protection below was already gone. But the stripping was not constant. That is one of MAVEN's most important findings. Atmospheric escape from Mars is episodic. It spikes during solar storms, when the sun sends a more intense pulse of radiation and particles outward. The stripping rate rises sharply during those events, then subsides, then rises again with the next storm. And here is where the damage compounds. The young sun was far more violent than the sun we observe today. Solar storms were more frequent, more intense. Early Mars did not just face the steady erosion that MAVEN measures now. It faced a much harder version of it, repeated across its most vulnerable period, while its atmosphere was still thick enough to lose in meaningful quantities. No single doomsday event was needed. Billions of years of exposure were enough. Repeated solar activity, no magnetic shield, and a sun that was angrier when Mars was young. The atmosphere was worn down episode by episode, storm by storm, era by era. And now, in 2025, something that scientists had suspected for decades was finally confirmed by a direct observation. NASA reported the first direct measurement of atmospheric sputtering at Mars. Sputtering is a specific escape mechanism, distinct from the broader solar wind stripping. Energetic particles slam into the upper atmosphere and physically knock individual atoms loose, ejecting them out into space. Think of it as a kind of atomic bombardment. Incoming particles collide with atmospheric atoms the way one billiard ball strikes another and sends it skidding off the table. The struck atom leaves the atmosphere entirely. It is gone. Sputtering had been proposed for decades as a significant contributor to early Martian atmospheric loss. The models suggested it was especially important when the young sun was most active, driving intense particle bombardment, but it had never been directly observed, not until 2025. NASA confirmed sputtering as a primary source of early atmospheric loss, particularly in that period of heightened solar activity when Mars was young and its sky was still thick enough for sputtering to carve deeply into it. Not theory. Direct observation. The sequence now had another mechanism added to it. Solar wind stripping, radiation, sputtering, all three operating simultaneously, all three amplified during solar storms, all three working across billions of years without a magnetic field in the way to slow them down. And modern Mars still shows exactly what an exposed planet looks like. Between May 20th and May 24th of this year, a significant solar storm reached Mars. NASA observed something remarkable: planet-wide auroras. On Earth, when a solar storm arrives, the magnetic field channels the incoming charged particles toward the poles. That is why auroras appear at high latitudes. The field guides the particles away from the bulk of the atmosphere and funnels them into a narrow zone near the poles. Mars has no such field. Nothing guides the particles anywhere. They hit the atmosphere wherever they arrive. And so, the auroras that appeared during that May storm were not polar phenomena. They covered the entire planet. The whole sky lit up. That is what being unshielded looks like. Not a polar glow. A planet-wide one. During the same storm, the Curiosity rover measured a radiation surge at the Martian surface. The reading came in at 8,100 micrograys. NASA put that number in terms anyone could feel. Standing on the Martian surface during that storm, a person would have received a radiation dose equivalent to roughly 30 chest X-rays. In a matter of days. It was the largest radiation surge Curiosity's radiation instrument had recorded since the rover landed. That number is worth holding. Curiosity sits on the surface, under the thin air, and that is what a single solar storm delivered. Not a catastrophic extinction-level event. Just a storm. The kind that will come again and again and again, because Mars has nothing to stop it. The picture now has all of its pieces. The magnetic field failed early. The solar wind and radiation found the unprotected atmosphere and began to strip it. Sputtering knocked individual atoms loose and ejected them into space. Solar storms drove repeated bursts of accelerated loss. The young sun made those bursts especially severe. And over billions of years, the atmosphere that once supported rivers and lakes, and a climate close to something habitable, was worn down to a thin, cold remnant of itself. Not one disaster. A long campaign. Storm by storm, atom by atom, era by era, until what remained was too thin to hold liquid water, too thin to hold heat, too thin to protect anything living on the surface below. Mars did not collapse in a moment. It was exposed for billions of years, and the sun did what the sun does to an unshielded world. What the planet became was the result of that patience, and the evidence of it is still arriving. Every solar storm that crosses the distance between the Sun and Mars adds another small entry to a record that stretches back to the beginning of the solar system. The planet is still losing what little remains, slowly, steadily, and without any sign of stopping. How much exactly? That question seems simple. After billions of years of atmospheric erosion, after solar storms stripping away atom by atom, the obvious follow-up is, how much water did Mars actually lose? And how do we know? The answer turns out to be more interesting than the question suggests. And the number that dominated the story for years may have been telling only part of it. In 2015, NASA released a finding that reshaped how almost everyone understood the Mars water story. Ancient Mars, the analysis concluded, once held more water than Earth's Arctic Ocean, a volume that large, a planet that wet, and roughly 87% of it was gone, lost to space over billions of years. That figure spread through science reporting and public understanding quickly. Mars had been an ocean world. Then the sun took it. The number was not invented. It was built from real evidence. But the technique behind it is worth understanding, because it is one of the more elegant pieces of forensic work planetary science has produced. Here is how it works. Water is made of hydrogen and oxygen. Most hydrogen atoms are ordinary. carrying a single proton in the nucleus. But a small fraction of hydrogen atoms are heavier. They carry an extra neutron. That heavier form is called deuterium. Water molecules built with deuterium instead of regular hydrogen are heavier overall. And when water escapes from a planet, the lighter molecules move faster and escape more readily. The heavier ones tend to stay behind. So a planet that has been losing water for billions of years will end up with water that is progressively enriched in deuterium. The ratio of deuterium to regular hydrogen, what scientists call the DH ratio, becomes a kind of chemical clock. A forensic fingerprint. You measure the ratio, compare it to what the original water would have looked like, and reconstruct how much hydrogen has escaped over time. Curiosity measured this. When the rover analysed water locked inside ancient rocks in Gale Crater, it found a lower DH ratio than the current Martian atmosphere carries. Ancient water, preserved in minerals, carried a signature closer to what the original inventory would have looked like. The modern atmosphere had been enriched over time as lighter hydrogen kept escaping. The gap between the two readings told scientists how much loss had occurred between when those rocks formed and now. And some of the loss happened even before those rocks formed. The history of departure was written directly into the chemistry of what remained. Multiple lines of evidence converged on the same conclusion. Landforms showed where water flowed. Minerals showed where it altered rock. The atmosphere showed the remnants of what once was thicker. And isotopes showed the fingerprint of what had been leaving. Together, those four lines pointed toward a planet that had once carried an enormous volume of surface water and had lost most of it. But then the story complicated. In 2021, a NASA-funded analysis looked at the numbers from a different angle. Researchers compared the estimated ancient water inventory to the measured rates of atmospheric escape and the volume of water still accounted for in ice and vapor. The totals did not balance. The escape to space, even added to the observable ice remaining today, was not enough to account for everything ancient Mars was thought to have carried. Something was missing from the ledger. The answer they proposed was the rock itself. A large fraction of ancient Martian water, possibly between 30 and 99% of the original inventory, may never have escaped to space at all. Instead, it was absorbed into hydrated minerals in the crust, chemically incorporated into rock. Hydrogen and oxygen bound into crystal lattices deep underground, locked away not by evaporation into the thin air, but by the slow chemical work of water reacting with rock over hundreds of millions of years. That range, 30 to 99%, is wide. Scientists acknowledge it is wide. The uncertainty reflects how difficult it is to reconstruct a water budget across 4 billion years from orbit and rover measurements. But the direction of the finding is clear. The simple story, where Mars had oceans and then the sun took them, was incomplete. Not wrong in all its parts. Incomplete. This connects directly to what Phoenix confirmed in 2008. The lander set down in the northern polar region and, when its thrusters disturbed the soil, exposed a bright material just beneath the surface. Over the following Martian days, that bright material disappeared. Not gradually, not like dust blown away by wind. It vanished in a way consistent with sublimation, ice converting directly to vapor in the thin air without passing through a liquid phase. The material was water ice, accessible, real, present at depths a shovel could reach. What that means for the modern water inventory is a three-part picture. Some water escaped to space, and the DH ratio records it. Some survived as ice, in polar deposits and in the shallow subsurface that Phoenix found. And some, possibly a large fraction, was absorbed into hydrated minerals in the crust over geological time, chemically locked into rock that is still there, still holding it. Mars is dry at the surface, but geologically, it is still a water world. The death of wet Mars was not a single disappearance, it was a partitioning. The water went to different places by different pathways on different timescales, and understanding which pathway dominated is still an open question. The 30 to 99% range reflects how open that question remains, but there is a more useful way to frame what ended. It was not the water that truly vanished first. Rivers need circulation to keep flowing. Lakes need stable temperatures to persist. Deltas need repeated flow events over long periods to build their characteristic shapes. A planet can hold a significant inventory of water and still lose the conditions that allow any of that water to move openly on the surface. What Mars lost, in the end, was not primarily molecules. It lost the climate system that kept those molecules mobile. That is the shift that matters. The rivers stopped, not because the last drop of water evaporated, but because the atmospheric pressure fell too low to sustain liquid water at the surface, because the temperatures swung too far, because the circulation that fed precipitation and replenished surface flow was broken. The water retreated into ice, into rock, into chemical bonds. It did not leave entirely. It became unavailable. And the question of exactly how much went where, how much escaped versus how much retreated into the crust, carries more than historical interest. Any future human presence on Mars would need to find and recover that water. The inventory is there. The partition is what will have to be understood. That part of the story is still being written. But here is something the story of loss does not prepare you for. Mars built the tallest volcano in the solar system. It raised a volcanic province the size of a continent. It carved the longest canyon system known anywhere. And then it failed to stay habitable. Those two facts sit in the same planet. Hold both of them for a moment. The standard account of Mars treats geological power and habitability failure as separate chapters. But they are not separate. They are tangled. Understanding why Mars failed requires understanding what it actually built and why building it was not enough. The Tharsis Rise covers roughly 5,000 kilometers from east to west and 6,000 kilometers from north to south. If you laid it across the United States, it would reach from the Atlantic coast to well beyond the Pacific. It is not a mountain range. It is not a volcanic field in any familiar sense. It is a province, a vast assemblage of lava flow fields and volcanic constructs so large it reshaped the planet's gravity field, deformed the surrounding lithosphere, and altered the tectonic stress patterns of the entire crust. The crust beneath and around Tharsis buckled under its own weight, the way a floor bends under a load placed at its center. Regional slopes changed. Stress fractures propagated outward. The way water could flow across the surface was altered by the presence of this single geological feature. And rising from that province, Olympus Mons, 25 to 26 kilometers above the surface, 3 times the height of Everest, already logged in an earlier section of this story. The number deserves repeating here, not as a curiosity but as evidence. Mars was not geologically timid. Mars was geologically extreme. The problem was not capacity. The problem was endurance. That distinction matters. A planet can accumulate enormous geological power and still fail to hold its conditions together. Capacity and resilience are different things. Mars had the first. It could not sustain the second. Then the data shifted. Volcanism on Mars may have briefly helped the planet stay warm. When volcanoes erupt on a large scale, they release gases into the atmosphere. Those gases can produce greenhouse warming, short-term warming, the kind that raises temperatures, melts surface ice, generates precipitation, drives fluvial activity. Scientists have found evidence suggesting that warm and wet conditions on early Mars may have occurred only occasionally, possibly triggered by large volcanic eruptions or by large impacts, not sustained, not stable, episodes, windows that opened and closed. Volcanic spikes warm a planet temporarily. They do not rebuild a durable climate. Mars had internal fire, but it lacked the full set of reinforcing systems that kept Earth's climate stable over billions of years. On Earth, a global magnetic field kept the atmosphere from being stripped. A thick atmosphere retained enough heat to sustain liquid water across long timescales. plate tectonics recycled carbon dioxide back into the mantle and then back into the atmosphere in a cycle that helped regulate surface temperature over geological time. Mars had none of those reinforcing systems in place when its volcanism was at its height. The eruptions generated heat and gas. The atmosphere leaked the gas. The heat dissipated. The window closed. Volcanic power without the surrounding stability can add instability rather than stability. That is not a subtle distinction. It is the difference between a climate that recovers from disruption and one that amplifies it. Then there was the bombardment. Early Mars was not just being reshaped from within. It was being hammered from outside. During the early Noachian period, the oldest chapter of Martian geological history, at least 65 impact basins larger than 150 kilometers in diameter formed on the Martian surface. That is not a quiet early history. That is a planet absorbing repeated catastrophic blows during the period when it most needed to hold its conditions together. Hellas is the most dramatic surviving signature of that era. A basin roughly 2,400 kilometers across, about 1,490 miles wide. The lowest elevations on Mars reach down to approximately 8,200 meters below the average surface elevation at its floor. It is deep, planetary trauma preserved in topography. An impact that size does not just leave a crater. It reorganizes the regional crust. It alters how heat escapes from the interior beneath it. It changes the atmospheric dynamics of an entire hemisphere. It can excavate buried ice, send steam into the atmosphere, generate transient warm conditions, and then those conditions fade as the energy dissipates. A smaller planet does not recover from repeated giant impacts the way a larger one does. Earth has been struck by large impactors too. But Earth's greater mass, thicker atmosphere, and active geological recycling gave it more capacity to absorb the damage and restabilize. Mars, with 1/10 the mass of Earth and faster cooling already underway, did not have the same reserves to draw on. Each major impact was a disruption the planet could not fully absorb before the next one arrived. The north-south dichotomy is one of the most visible relics of that era. The southern hemisphere of Mars is ancient, heavily cratered highland terrain. It is some of the oldest surviving surface in the solar system. The northern lowlands are smoother, lower in elevation, and much of whatever earliest history they carried has been buried or erased. Topographic data from the MOLA instrument, the Mars Orbiter Laser Altimeter, shows a broad regional slope from the high southern terrain down to the low northern plains. The origin of this dichotomy, whether it formed from a single giant impact in the north, from early tectonic processes, or from some combination, remains debated. But the result is a planet that may have been structurally lopsided from the very beginning, one hemisphere carrying its deep ancient record, the other hemisphere's early story largely gone. But here is the part that cuts against the simple story of pure destruction. The same impacts that destabilized Mars also created some of the best evidence for ancient water we have found. A large impact heats subsurface rock. It melts buried ice. It generates hydrothermal circulation, water moving through hot fractured rock, sometimes for thousands of years after the impact itself. It creates a basin. Basins fill, lakes form, sediment accumulates at the bottom. Minerals precipitate from the water and preserve their chemistry in the rock. Jezero Crater is one example of that process, covered earlier in this account. The ESA survey of water-related minerals across the Martian surface found 175 sites with hydrated minerals associated specifically with impact craters, distributed across crater walls, rims, ejector blankets, and central uplifts. Crater sizes in that survey ranged from less than 1 kilometer to 84 kilometers across, exposing material from tens of meters to kilometers below the original surface. The impacts bored down through the crust and brought the subsurface record upward where instruments could read it. Impact craters were not only scars, they were, in some cases, temporary habitats, and they are now geological archives. That is the paradox of early Mars. The forces that made sustained habitability nearly impossible were also the forces that created the brief windows of liquid water we can still read in the rock. Volcanism drove short-term warming episodes. Large impacts generated temporary hydrothermal systems and lake basins. Both left chemical evidence that Mars was once, in places and at times, a world where water moved and minerals formed in the presence of that water. And both were forces a smaller, faster cooling, magnetically unprotected planet could not convert into long-term stability. The brutal truth of early Mars is that it had an extraordinary amount of geological energy, and almost no way to channel that energy into the conditions life needs most. Not a single wet episode. Not a moment of warmth. Years, centuries, perhaps millions of years at a time. But not the sustained stability that Earth maintained across billions of years. The fires burned hot and then they went out, and when they went out, there was nothing left to hold the atmosphere. Nothing left to keep the water moving, nothing left to absorb the next blow. What geology gave, geology also took away. And the geological story of Mars is not finished surprising us. Follow what happens after the early chaos settles. The volcanic eruptions slow. The impact bombardment thins. The heat escapes into space and does not return. And what remains is not a frozen, static world waiting quietly in the dark. What remains is a planet that has changed character. It is still moving, still cycling, still doing something. Just something completely different from what it did before. There is no single day when Mars stopped being a world with widespread surface water. The geological record does not have a clean edge. But the United States Geological Survey has mapped the transition closely, and by the end of the Noachian period, roughly 3.7 billion years ago, the rates of impact, valley formation, weathering, and erosion had all dropped sharply together. Not gradually fading in isolation, all of them dropping at the same time. The whole system became less capable of supporting widespread liquid water at the surface, not less water here and there. The entire machinery that kept water in motion shut down. What came after was not stillness, it was oscillation. Mars still has an axial tilt similar to Earth's. That tilt gives Mars seasons, just as Earth has seasons. But Earth's axial tilt stays relatively stable over long timescales, held in check partly by the gravitational steadying influence of the Moon. Mars has no such anchor. Its tilt swings far more dramatically over tens of millions of years. Planetary scientists call this obliquity variation. Think of a spinning top wobbling slowly as it loses speed, shifting the angle at which it tilts before recovering and tilting again. Mars does something like that, but across enormous spans of time. During periods of high tilt, the polar and near-polar regions receive more direct sunlight. They warm. They release water vapor. NASA research suggests that during these high obliquity phases, soils near the poles may even support thicker, liquid-like films of water along mineral grain surfaces. Not rivers, not lakes, but the conditions for chemistry, changing and responding. This is the picture of later Mars, not dead, oscillating. A slowly wobbling climate driven by shifting sunlight, ice migration, and the exchange between the atmosphere and the poles. The poles hold a record of this oscillation. Radar instruments on spacecraft orbiting Mars have mapped the internal structure of the polar ice deposits by sending signals down through the ice and measuring how they bounce back. What the radar shows is layering, alternating bands of ice and dust, stacked the way pages stack in a book. Each band represents a different climate state, a different balance of dust in the air and ice on the ground, driven by the changing tilt and changing orbit. The North Polar layered deposits contain stacked units that shifted over the past few million years. The estimated age of the North Polar Cap based on these radar reconstructions is roughly 4 million years. 4 million years of climate history preserved in frozen layers, waiting to be read. The poles are not just reservoirs of ice, they are climate archives, and the archive shows a Mars that never stopped responding to the forces acting on it. But the poles do something else that has no real parallel on Earth. When one hemisphere of Mars enters winter, carbon dioxide freezes directly out of the atmosphere and falls as dry ice onto the polar cap. Not a little, not a trace. Roughly 3 to 4 trillion tons of carbon dioxide, frozen out of the air every winter. That is somewhere between 12 and 16% of the entire Martian atmosphere by mass, cycling onto the poles and back every year. On Earth, winter does not park a significant fraction of the atmosphere on the poles as dry ice. On Mars, it actually does. The atmosphere itself breathes in and out with the seasons, swelling and thinning as carbon dioxide migrates from air to ice and back again. The atmosphere is so thin and the cold so extreme that the seasonal cycle carves deep into what little air remains. Something else was happening. Once the surface water system was gone, once the rivers and lakes had retreated and the thick atmosphere had thinned, something else moved into the center of the climate story. Dust. On Earth, dust is weather in the background. On Mars, dust is the engine. NASA and JPL describe Mars as a world of local dust storms, regional dust storms, and periodic global dust storms that can engulf the entire planet for weeks or months. Dust devils, whirlwinds that form when warm air rises and spirals, are not occasional events. They are routine. They are daily. Perseverance landed in Jezero crater in February 2021, and in its first roughly 200 days of operation, it recorded some of the most intense dust activity ever directly observed on Mars. At least 4 dust-bearing whirlwinds per typical Martian day. More than 1 per hour during peak activity. Gusts that lifted dust clouds covering roughly 4 square kilometers. About 1.5 square miles in area. Not extraordinary conditions for Jezero. Ordinary ones. The scale of Martian dust events extends far beyond individual whirlwinds. In early 2022, NASA reported a regional dust storm nearly twice the size of the United States, spreading across the Martian surface. The InSight lander, still operating at the time, had to enter safe mode. Dust reduced sunlight reaching the solar panels, cutting available power. The Ingenuity helicopter delayed its flights. One storm. Hundreds of millions of square kilometers. Instruments shutting down across the planet. Dust is not cosmetic weather. It changes the heating of the atmosphere. It changes circulation patterns. It changes what the surface receives in terms of sunlight. It can end the operational life of a solar-powered spacecraft. But dust does something more specific than disrupt operations. It helps complete the process Mars has been running for billions of years. Dust storms loft water vapor much higher into the atmosphere than normal conditions allow. The storms heat the upper atmosphere, preventing water vapor from freezing out at lower altitudes, letting it climb farther up than it would otherwise go. At those high altitudes, ultraviolet radiation from the sun breaks water molecules apart. The hydrogen, freed from the water molecule, escapes into space. The oxygen is left behind or lost through other processes. Every major dust storm is, in a small but real way, part of the drain. Dust does not just move material around, it helps Mars continue losing water. And then, in late 2025, NASA reported something that scientists had long theorized, but never confirmed directly. Perseverance had recorded electrical discharges inside Martian dust devils, and storms, sparks, and mini-sonic booms. The SuperCam instrument, which carries both audio recording and electromagnetic sensing capability, logged 55 distinct electrical events over the course of the mission. 16 of them occurred during direct dust devil overpasses, when a whirlwind passed directly over the rover. Not suspected, not modeled, directly recorded, with sound and electromagnetic signatures. Martian dust devils are not just spinning columns of grit. They are charged. They generate electrical fields. They crack with small discharges. They pop with shockwaves. The chemical consequences of electrically active dust are still being studied. What it means for organic molecules near the surface, for the breakdown of certain compounds, for the behavior of fine particles in the thin air, Those questions are open. But the dust itself is more active than any previous picture of Mars suggested. Mechanically active, electrically active, chemically relevant. Think about what that means for the picture of modern Mars. The surface water is gone. The thick atmosphere is gone. The geological fires have cooled. What remains is a planet still running a climate system, still cycling material between the poles and the air, still buffeted by seasonal swings that freeze out a significant fraction of the atmosphere every winter, still swept by storms large enough to bury continents in dust, still sparking. Modern Mars is not a frozen rock waiting in silence. It is restless. It is thin and cold and dry, but it is restless. And the full story of what that restlessness is doing to the planet, and what it means for anything that might try to survive there, is still coming into focus. That restlessness is still with us as we turn inward, toward the deepest question the entire script has been circling. The question of whether Mars ever had life used to be a science fiction question. It was speculative, almost philosophical, a matter of imagination rather than evidence. That is no longer where the field stands. Mars has organic molecules preserved in ancient rock. Mars has a methane signal that returns with the seasons. Mars has sediment samples carrying features that resemble what biology leaves behind. The question has not been answered, but it has been transformed. It is no longer mainly a question about whether Mars was the right kind of place. We know it was the right kind of place, in some locations, at some times. The question now is forensic. Did anything actually use those windows? Curiosity has been monitoring methane in Gale Crater for nearly 3 Mars years. The pattern it recorded is repeatable. Methane rises in warmer periods and falls in colder ones. It cycles. It behaves as though something is producing it on a schedule tied to temperature. On Earth, most methane comes from biology. Microbes, organic decay, living systems. But methane can also form through water reacting with rock at certain temperatures and pressures. That process requires no biology at all. NASA's careful wording reflects this exactly. Water rock chemistry might explain the methane, and biology cannot be ruled out. That is not a hedge. That is the honest statement of where the evidence stands. Important, not decisive, and not all of early Mars was equally promising. Opportunity spent years exploring Meridiani Planum, a broad flat plain far from Gale Crater. What it found there kept the story honest. These sedimentary rocks at Meridiani formed in ancient ephemeral playas, shallow temporary pools that filled and evaporated. Mixed through the rock were small hematite spherules, iron-rich balls that formed when acidic groundwater rose through ancient sediment. They got a nickname, blueberries. They are scattered across the surface like gravel. They are beautiful. They are also evidence that some ancient Martian water was acidic and chemically harsh. Not the moderate, low salinity conditions Curiosity found in Gale. Different chemistry, different story. Mars did not have one ancient water environment. It had many. Some with mild chemistry and persistent lakes. Some with acidic groundwater and short-lived pools. The habitable windows that existed were real, but they were scattered across the planet unevenly. Mars had many water stories, not one. Then came 2025. NASA reported that Perseverance had drilled a sample from a rock called Chayava Falls in Jezero Crater. The sample, designated Sapphire Canyon, contains what NASA described as potential biosignatures. The rock's features may reflect chemical reactions that could once have supported microbial life. Non-biological explanations are still being considered. Those are NASA's words, used with precision. Not proof of life, not even probable life, potential biosignatures. But that phrase carries weight. It is the most serious wording the investigation has produced. It means the features in this rock are the kind of features biology sometimes leaves behind. It means no one can cleanly rule life out by looking at the chemistry. The field has crossed a threshold. The conversation is no longer about whether Mars had habitable environments. It is about whether specific rock samples preserve traces of ancient microbes supporting chemistry. It is a detective question now. Evidence, not speculation. The case is strong enough to make the question legitimate. It is not complete enough to close it. So we leave it open. And we build the full picture of how the planet failed. The clean version of that story runs like this. Mars started with enough internal heat, atmospheric thickness, and water activity to support rivers, lakes, groundwater, and chemically plausible environments for microbial life. But Mars was smaller than Earth, 1/10 the mass. That made it faster to cool, easier to lose dynamo conditions, easier to suffer atmospheric erosion. The clean chain is direct. Smaller mass meant faster cooling. Faster cooling meant a weakening internal engine. A weakening engine meant the global magnetic field declined and eventually collapsed. Without that shield, the atmosphere faced the solar wind without protection. The atmosphere thinned. Surface pressure dropped. Liquid water became unstable. The climate slid away from the conditions that had allowed rivers and lakes to exist. But the real version is messier. Volcanism built Tharsis and raised the largest volcanoes in the solar system. Those eruptions contributed atmospheric gases and temporary warming that extended wet periods beyond what internal heat alone could sustain. Impacts reshaped the crust, triggered short-term hydrothermal systems, and opened new lake basins even as they made long-term stability harder to maintain. Mars's axial tilt shifted dramatically over tens of millions of years, moving ice around, changing where water was accessible, creating brief windows of increased water vapor even in the deep cold. Dust became the main engine of the modern climate, and water did not simply vanish. Some escaped to space. Some froze into polar ice and subsurface permafrost. Some locked permanently into hydrated minerals in the crust. The system degraded. It did not switch off. Mars did not suffer one apocalypse. It underwent a long systems failure. The interior lost long-term power. The magnetic shield shut down. The atmosphere became easier to strip. Stable surface water became harder to maintain. The climate shifted into a thinner, harsher, more variable mode. Each step made the next step more likely. Each protection that fell made the remaining protections harder to sustain. Water still exists on Mars today, frozen in the poles, locked in rock, buried as permafrost. But the full system that kept water mobile and available across the surface for millions of years collapsed piece by piece over billions of years. Earth still has all of those protections. A global magnetic field generated by an active core. A thick atmosphere reinforced by a plate tectonic carbon cycle that recycles greenhouse gases back into the air. Long-term climate buffering that resists sharp, permanent transitions. An active hydrological cycle. Stable surface conditions for life across geological time. The difference between Earth and Mars is not simply that Earth got lucky. It is that Earth maintained planetary resilience, the full set of interconnected systems that reinforce each other and absorb shocks, while Mars lost it layer by layer. The old picture was simple. Earth alive, Mars dead. One world succeeded, one world failed. The new picture is harder and more important. Mars got most of the way there. Moving water, river deltas, lake beds, groundwater reaching deep into the crust, moderate chemistry in some places, preserved organics, possible biosignatures sealed in a rock waiting on the floor of Jezero crater. Mars was not a failed rock. It was a world close enough to habitability that its collapse is scientifically precise and worth understanding fully. Perseverance carried 43 tubes to Mars, 38 for sample collection, 5 as witness tubes, unsealed controls that record the ambient environment at Jezero for comparison. The mission planned to collect roughly 30 samples overall. Some of those tubes are already filled and sealed, waiting on the Martian surface. NASA's Mars Sample Return campaign remains a priority. In January 2025, NASA said it was refining the architecture through 2 possible landing approaches and expected to confirm the program and its design in the second half of 2026. The best evidence in the investigation is still on another planet, sealed in tubes, sitting in a crater that was once a lake. Those samples could tell us whether the most promising Martian environments were only chemically favorable or whether they preserve something more. That question remains open. The evidence chain is still being built. Mars is what happens when a world that once looked survivable loses the invisible systems that protect habitability. It still has the scars of ancient rivers in its highlands. It still has the dry deltas where lakes once reached their edges. It still has buried ice and minerals that locked water away billions of years ago. It still has, possibly, the chemical traces of the most consequential thing that ever happened there. What it no longer has is the full set of planetary protections that kept a world open for surface life across geological time. Mars is not only a story about another planet's past, it is a case study in how fragile planetary futures can be.